Let's continue talking about our ladder operators for the angular momentum for the electron and the hydrogen atom. Um, so the bottom rung eigenfunction that we'll denote with a B, so FB, is going to work so that it terminates our ladder operator. So if we try to use the lowering operator once more, we get an answer of 0, and it terminates that series. So we can go ahead and define the eigenvalue for our z component of our angular momentum to be h bar, and we'll call that L bar, so that when our z component operator acts on this eigenfunction at the bottom, we get that lowest eigenvalue. And then, of course, for our angular momentum squared, we're going to get that same old, we called it lambda eigenvalue from this eigenfunction. So in a similar way as to how we did the top rung, we can figure out that our eigenvalue for our angular momentum squared should equal h bar squared L bar times the quantity L bar minus 1. So if we compare our top rung answer for our eigenvalue for the angular momentum squared and our bottom rung answer for that angular momentum squared eigenvalue, we're going to get that either, well, we're going to get, let's do one thing at a time. Let's give it the right color. All right, we're going to get either L times the quantity L plus 1 equals L bar times the quantity L bar minus 1. So that says that either L bar has to equal, back that up, L bar has to equal L plus 1, or L bar has to equal minus L. So what do these two things say? Well, the first option here says that the bottom rung is higher than the top. That doesn't make much sense. So we're probably going to reject this solution. And this one makes a little more sense, that the bottom rung equals negative the top rung. So we're going to use that second one. And then we're going to say that the eigenvalues of our operator LZ are going to be an integer times h bar, where, and this isn't necessarily an integer, but it goes in integer steps, where m goes from negative L to positive L in a certain number of integer steps. Then we know that L could be written as negative L plus N. And L is N over 2. The result of this solution is that L either is an integer, so it must be an integer, or a half integer. From these eigenvalues of LZ being M and M being confined to these L in steps. Okay, so that bottom rung leads us to our eigenfunctions being characterized by L and M. So if our eigenfunctions are characterized by L and M, that just means that we want to denote which function we're talking about in relation to L and M. And in particular, if we have our angular momentum squared acting on an eigenfunction that depends on L and M, it's going to return an eigenvalue that looks like h bar squared, L plus 1. And that's with the eigenfunction that's dependent on M and L. So we can see that the angular momentum squared is only really depending on L there for the eigenvalues. In the meantime, the operator that has to do with just one component of our angular momentum, acting on an eigenfunction L that depends on L and M, is going to return a eigenfunction h bar times, or an eigenvalue h bar times M, acting on that eigenfunction that has to do with M and L. Now this doesn't look like it depends on L, but remember L gives us our limits of what M can be. So in this case, L could be 0, 1/2, 1, 3/2, and so on. And meanwhile, M would be a negative L all the way up through 0 to your positive L. So for a given value of L, you're going to have a number of values of M. You're going to have 2L plus 1 possible values of M. So this L, remember, has to do with our angular momentum squared, and this M is having to do with this LZ, or this one component of our angular momentum. You can visualize this. It's not a perfect visualization, but you can visualize this in figure 412 in the newer edition of the book. It's 409 in the older edition. So in this figure, we start off with, let's give ourselves some axes here. So we start off with an x, y, and z axis where we're looking at these components of the angular momentum. And so in this, we actually see that we scribe out a sphere. And that sphere has a radius that looks like our allowed value of L squared. So the length of this value is actually our radius of the sphere is in the neighborhood of the square root of L times the quantity L plus 1. And then there are certain allowed values. So as you step up and down in this operator, and they're scribed out like they're cones, right? There are these cones of uncertainty at these different levels that our LZ goes up or down with that ladder operator. And that has to do with those eigenvalues that are h bar times M or M times h bar, either way. And in general, we see that the square root of L times quantity L plus 1 is usually greater than L. So this radius of the sphere is usually greater than the max LZ. So we never get perfectly along this LZ axis with our ladder operators. And that's not because we chose LZ incorrectly. That is just a function of the uncertainty. right? If you were perfectly along the z direction, that means you know Lx and Ly are 0 simultaneously, and you know Lz simultaneously. And we already saw that those were incompatible operators. So this is a bit of a misleading diagram. You've got to remember that there aren't definite Lx, Ly, and Lz simultaneously. So those cones of uncertainty that are drawn are a little bit more interesting. So what we've done so far is we have determined some eigenvalues in terms of those quantum numbers for our angular momentum squared and for one component of our angular momentum without actually finding the eigenfunctions. So those eigenfunctions are going to lead us to the functions being the spherical harmonics. And the spherical harmonics are orthogonal because they're eigenfunctions of Hermitian operators. So we're going to get to finding that these eigenfunctions that we denote it with M and L are actually those spherical harmonics that we've already seen. And we'll start with that one next time.